You've probably seen this dozens of times without ever thinking about it. A semi-truck or a bus passes you on the highway, and there's a thin tube or hose attached to the wheel spinning along with it. It's exposed to dirt, water, road salt, vibration. It looks fragile, almost improvised, like a temporary fix or a homemade modification, but it isn't. That small tube is part of an engineering system that directly affects the truck's stability and safety. And here's the dangerous part. When it stops working, the truck doesn't stop. It keeps rolling. That's where the real risk begins, because the stability of a multi-ton vehicle is not defined by the engine or electronics. The entire weight of the truck, tens of tons of steel, cargo, and fuel, is transferred to the road through just a few contact patches, each about the size of a hand. The tires are the truck's only physical connection to the asphalt. When tire pressure drops, even slightly, the geometry of that contact patch changes. The tire deforms more. The sidewalls start operating outside their designed range. Rolling resistance increases, and heat builds up inside the carcass. This directly affects stability. During braking, lane changes, and cornering, forces are no longer distributed the way the engineers intended. The vehicle becomes less predictable, especially at highway speed and under full load. And the most dangerous part? This process starts long before a tire looks flat. Central tire inflation systems didn't appear in civilian transport, and they weren't created for driver convenience. Their origins are military. During World War II and in the decades that followed, military engineers faced a critical problem. Heavy vehicles had to move across asphalt, dirt, sand, mud, and even exit water directly onto shore without stopping. Stopping to manually adjust tire pressure meant losing time and exposing the crew.
The concept was simple, but the execution wasn't. Give the vehicle the ability to change tire pressure while moving. Hard surface, higher pressure. Soft terrain, lower pressure. Lower pressure increased the contact patch, reduced ground pressure, and dramatically improved mobility. Only later did this principle move into civilian use, first in specialized equipment, then in buses and heavy trucks operating in harsh conditions. From a systems perspective, CTIS is surprisingly straightforward. A truck already carries a source of compressed air, the compressor and air reservoirs that supply the air brakes and suspension. CTIS uses the same air, but through separate circuits and priority protection valves. Each wheel is connected to the system through a pneumatic line. Sensors constantly monitor tire pressure. If pressure drops below a preset value, the system automatically adds air, restoring it to a safe operating range. What's important to understand is this. The system is not trying to fix a puncture. Its job is to stabilize the situation, slow down the failure, prevent overheating, and buy time so the driver can safely stop or reach a repair location. That raises an obvious question. Why is such a critical system mounted externally instead of being hidden inside the hub? The answer is reliability. Internal solutions require complex seals operating in extreme heat, dirt, moisture, and under high centrifugal loads. In real-world heavy-duty conditions, those systems wear quickly and are expensive to repair. An external hose with a rotating air union is mechanically simpler. Between the stationary axle and the rotating wheel sits a sealed rotary joint, working like a bearing. The inner section remains fixed. The outer rotates with the wheel, while air flows through without leaks. It's easy to service, quick to repair in the field, and keeps working where more elegant solutions fail.
A loss of pressure in a truck tire rarely looks like a sudden blowout. In the vast majority of cases, it starts quietly, with a small leak. Pressure drops by just a few tenths of a bar. Visually, the tire still looks almost normal. Its shape seems intact. There are no obvious external warning signs, but physics has already taken over. As pressure decreases, the tire begins to deform more in the contact patch. The sidewalls flex beyond their intended design range. Internal friction between the rubber and the cord layers increases, and that friction generates heat, not gradually, but exponentially. Lower pressure leads to more deformation. More deformation leads to higher temperature. Higher temperature accelerates structural breakdown. This process can unfold over dozens of miles while remaining almost completely invisible from the outside. That's why pressure loss is one of the most deceptive failure modes in heavy-duty vehicles. Why the driver often doesn't feel the problem until it's critical. A truck is not a passenger car. Its mass, long wheelbase, and air suspension naturally filter out small changes in handling. The most dangerous phase is the transition zone. The tire is already overheated. Its structural strength is significantly reduced, but the vehicle still feels acceptable to drive. This is where sudden failures occur. Sidewall rupture, bead unseating, or a high-speed tire explosion. To the driver, it feels like something happened instantly, even though the failure had been developing for a long time. Will the system keep pumping air into the tire indefinitely? No. A central tire inflation system is not designed to repair a damaged tire. Its purpose is to stabilize pressure and slow down the escalation of a dangerous situation. When pressure begins to drop, the system automatically supplies air to compensate for the leak. This helps to maintain the tire's shape, reduce sidewall deformation, limit heat buildup, preserve vehicle control. But if the damage is serious, a sidewall rupture, a large cut, or structural cord failure, the air escapes faster than the system can supply it. At that point, inflation becomes ineffective. The system either shuts down automatically or simply can't keep up. This is critical to understand. The system does not fight physics. It doesn't try to save the tire at any cost. It only keeps the situation within a controllable window, for as long as that's physically possible. Why brakes always have priority over the tires? A truck uses a single pneumatic system to supply multiple critical components. First and foremost, the brakes. That's why these systems are designed with strict priority logic. If air loss becomes significant, a protection valve immediately cuts off air supply to the tire inflation system. Central tire inflation systems are not universal. They didn't appear and spread simply because the technology exists, but because in certain conditions, operating without them becomes an unacceptable risk. That's why the geography of CTIS use is so revealing. United States. In North America, the key factors are distance and speed. Highways stretch for hundreds and even thousands of kilometers. Average cruising speeds are high, and heavy truck combinations operate under constant load. In these conditions, a sudden loss of tire pressure becomes especially dangerous. The nearest service point can be tens of kilometers away, and stopping on the shoulder is far from always safe. Australia is almost an ideal example of an environment where CTIS becomes vital. Vast distances, minimal infrastructure, high temperatures, and poor road surfaces. Here, tire inflation systems are not an option, but a matter of survival. They allow pressure to be adapted to the surface, reduce the risk of getting stuck, compensate for small leaks, and keep the vehicle moving toward a service point that may be hundreds of kilometers away. Europe presents a different situation. Shorter distances, a dense service network, high-quality roads, and strict requirements for the safety of other road users. External hoses and tubes are considered potentially hazardous elements. They can be damaged or pose a risk to motorcyclists and pedestrians. That's why Europe more often relies on tire pressure monitoring systems, TPMS, which warn the driver but do not interfere with wheel operation. The conclusion is simple. CTIS is neither better nor worse than the alternatives. It is perfectly suited for certain conditions and unnecessary in others. Simple on the outside, rough in appearance, but completely logical on the inside. That's what technology designed for real-world operation looks like, not for display. And one final question. Have you ever wondered why some trucks have wheels that don't even touch the road? Why they hang in the air? I already have a separate video about that. Make sure to watch it.